So, of course, my goal here is not as much as presenting specific designs or specific solutions, but to show you how simulations can help solving the problems that most of you may have using our software tools, which are commercial, which I think I call where rubber meets the road, because these tools are used all over the world by many users, and so they're well tested for the real world conditions. So I'll start with an introduction to Altair, because some of you may not be aware of what Altair does, and then specifically Altair electromagnetic simulation tools, and then we'll go into 5G, what 5G means to us now, and have a case study of an antenna design for the devices as well as the base station. And also we talk about the channel coverage analysis. This is something is becoming more and more critical with a lot of wireless coverages coming in, and also the complex scenarios that need to be taken into account. Because for 5G, beamforming is becoming, is the key. And we'll talk a little bit about that, what difference it makes in the coverage analysis, but also different types of beamforming, for example, envelope beam pattern type of analysis, as well as Monte Carlo analysis, and then we'll conclude. So with that, about Altair, it is not a new company. It has been established in 1985, almost 35 plus years in Troy, Michigan. It's a small company, actually. 3 people started the company at that time. And of course, it's now grown to as an international company with 86 offices in 25 countries with 3,000 plus. So this is, of course, last year numbers. I think we are growing very rapidly, so I wouldn't be surprised. This is much higher number now than 3,000. Same thing with the customers. We have customers all over the world. Of course, this is also last year number, 450 million revenue for last year, almost $500 million there. And also we have a lot of software partners that we work with, 150 plus partners there. So in terms of our operations in India, I would say this is one of the largest operations we have outside of the US, the Indian operations based in, headquartered in Bangalore, but I have offices in Pune, Delhi, Chennai, and Hyderabad, and many other places. And so they cater to all our customers there in various domains. As you can see here, we cover a wide spectrum of domains, not just electromagnetics is one of them, very key of them, but rest of the things as well from India. So overall, 11,000 plus customers. If you look at the portfolio, every industry you can think of, we have customers there, key customers in that portfolio. So why is this? This is the case because of the broad solutions portfolio we have. This is even, of course, we can dig into this. Each one can become its own presentation. So we start with the design, modeling, and visualization. This is where your concept design can start with. Then you can have physics simulations that, for example, electromagnetics, structures, and those kind of things. And then data analytics. This is also covering artificial intelligence as well as machine learning. And then Internet of Things. This is the physical layer to the cloud interface software that we actually provide, and as well as high performance and cloud computing. Not only the physical compliance, the appliances where you can have physical clusters, we provide them, but also we provide cloud services where all our software can run on the cloud. And of course, as I mentioned, we have partner ends where we work with various partners. So if you look at the physics-based portfolio, it starts with a system simulation. This you can think of as a 1D modeling of the system where you can have a block diagram and be able to do the system analysis. So it's not the electromagnetics right now, but probably could be in mechanical side. We do those kind of things very efficiently. And then manufacturing simulations. These are the extrusions and molding and those kind of things. Before you do them, you want to simulate and then see that your molding works fine, your extrusions work fine, and those kind of things. Electromagnetics that we talk a little bit more today's talk. and structural analysis and crash safety impact, thermal, fluid dynamics. The whole spectrum of physics is covered here. And also, they're all linked to optimization. That is, all of them can be optimized in a multi-domain, multi-physics scenario. So coming to electromagnetic simulations, of course, we have two main, I would say, disciplines of simulations. One is Altair Feko, where the traditional computational electromagnetics is applied. Other one is Altair WinProp, where propagation analysis applied. We'll talk a little bit more about these things because though they all follow electromagnetics in terms of Maxwell's equations, how they can handle things, because here we're talking about all the details here. Here we're talking about a huge city with terrain and all those things. Obviously, you cannot apply the same techniques that you apply here into this kind of scenario. So there are techniques which can give you reliable answers for these kind of large scenarios as well. So these can all, they both can help in 5G simulations when we get there. So in terms of 5G, of course, the question is, why do we need 5G? And some of it is covered in yesterday's talk as well. I want to give my perspective on this one. So I picked up this graph from a recent presentation at IMS conference. If you go to, of course, back in 70s, obviously we did not have internet. Even 90, before 90, we did not have any internet. So it started in 90s. I don't know, some of you are old enough to remember this one. It's called Mosaic. This is the first internet browser that came out from University of Illinois, the supercomputing center. This is more like, research project type of thing. I'm proud to say that I was one of the users of Mosaic when it came out. Then, of course, came, we don't have it here. Some of you remember Netscape. Of course, that also disappeared in thin air. Then, of course, Google came. So if you look at the data consumption by the users, petabytes per month. By the way, I think petabyte means 10 to the power of 16. Terabyte is 10 to the power of 12, and gigabyte is 10 to the power of 9, and petabyte is 10 to the power of 16. So it's almost nothing here in 1995. When it gets to 2000, around 80 petabytes per month consumption by the users. Then came, of course, eBay and other kind of things, and now we can see that 2,400 petabytes, and very quickly in 2010, with, of course, streaming services, 20,000, and of course, 2015, it's around 80,000 here. Obviously, it's grown so dramatically, you can't measure them in petabytes, so you start measuring in zettabytes. Actually, I had to look up and see what is zettabyte means. It's 10 to the power of 22. Of course, there's one step between them is exabyte, that is 10 to the power of 19. So you can see the exponential growth in the data that is consumed. Even today, I think this graph was presented in the middle of the year, so probably the data is a little bit outdated. Because of the COVID, potentially this could be even double the number. I would be surprised about it because everything became virtual and data is consumed like we're doing now in a very expedited way. So evolution of, so to look back, I guess, what happened in the past. Again, yesterday we had a little bit of overview of this one from the talk yesterday, but I want to again put my perspective here. Of course, 1G, you can think of like, one is walking, 2G is like, someone is running, 3G, maybe you're going in a bicycle, 4G is like you can go in a car, 5G is like going in a plane. So you can see the distinction, I guess, in these things, that the difference between how much time it takes to go by a car versus flying into a place. But also at this point, I want to comment, I guess, that you can't go everywhere by a flight, I guess, right? If you want to go next door, you don't want to take a car or you don't want to take a flight, you take a bicycle, or maybe you walk or you run. So there is a place for all these things in the real life, I guess. So one solution may not work for everything else, which we'll talk also later on. Why 5G may work for some situations and may not work for others. So if you take the handsets going from 83, and then all the way to 2019. This is actually Samsung's 5G phone that came out last year. You can see that from some of these things, you have this stub that acts as an antenna, stub with they used to call it stub antenna here, so more like a monopole type of thing. And slowly it started disappearing when 3G came out with a smartphone, as well as 4G later on, of course, 5G. You don't see any antennas here. Because our interest here is that from antenna perspective, they became external to internal, single band to dual band, multi-band and multi-band antenna. And of course, now with 4G, the diversity, as well as with 5G, the massive MIMO type of thing. So when we develop successful 5G, the expectation is that you'll have campus networks that are very efficient and high speed, as well as some of the new applications that are coming up called car-to-car communications or car-to-infrastructure communications. They were considering 5G to be the key in doing some of those things. And also, apart from our consumer side of it, industrial IoT, this is where machines talk to each other, or they also call it Industry 4.0. This is going to make a difference in with 5G evolution. So challenges for 5G. Of course, we all know the good things about 5G, that we want 10 times the data rate that we have, massive growth of the connected devices, latency for real-time connections, and high energy efficiency, longer battery life, and so on and so forth. Also connected cars, machine-to-machine communications. So this actually has three, though I'm putting some frequencies here, you can think of the three bands. Below 1 gigahertz for basic coverage, and then 3.5 gigahertz for high data rate service and capacity, 26 gigahertz for fiber-like connections, that is, high data rates. So you can call it low band, mid band, and higher band here in millimeter wave band there. So again, going back to the same one, why we need to have these three bands. If you look at the low band here, these frequencies waves are penetrable into the trees and the buildings and those kind of things. So they're very good for those type of applications. Once you start getting into mid band, they are penetrable, but not as good as the low frequency here. And then, of course, when you go to the higher band, most of the time it's line of sight type of application. So it has very limited coverage type of thing. So, yeah, and then of course there's also plans to go beyond 5G, that 6G going to terahertz, which I think in my talk I'm not going to talk about it, but that's also something people are considering for very close connections, I guess, because they have the same disadvantage as this high band, even more so because of the some of the things we talk about, atmospheric absorption and those kind of things. So we know that 5G uses massive MIMO. So let's take a very simplistic view of what is massive MIMO. If when the initial phones came for 1G, 2G, and 3G also, there's a sub antenna. The antenna pattern looked like this. There's an omni pattern here. So when the 4G LTE came, MIMO became more important there. It's multiple input, multiple output. That means you have not only one antenna, similar to what it is here in the one, and a second antenna for polarization diversity, and maybe more. But they're all omni patterns, but with the different orientations and for pattern diversity and those kind of things, but also locations so that they can receive the various multipath rays or the signals, so they can combine them to be able to have a much more data rate than what the one antenna can provide for us. So when it comes to 5G massive MIMO, you can think of it, instead of having a omni pattern, you want to have an array that is very pointed. So you have a pointed beam, not only one, but you also want to have two. That is the second one, again providing the pattern diversity. So now the challenge is to integrate instead of just single antennas, the arrays into the device. And then, of course, on the base station as well, you have an array with a pointed beam. So you can think of as a beam pointing directly to the mobile handset. So providing you almost like a point-to-point communication data rates, because all energy is focused on one device. And this device is, again, pointing to the base station. So you have a very reliable connection there. So just as a summary, I guess, 4G could be thought of as, covering everything here. And of course, 5G, we have multiple beams that are covering individual users and individual locations here. So that's kind of, you can think of as a massive MIMO. I know we picked the same picture from yesterday's talk and now from the probably same website here. So beamforming, now you can think of it as a macro cell where you can use 4G, for example, to cover wider area. But then when you come to the smaller cells, you can now have beamforming with large arrays that can actually serve individual users, like a person here and moving cars, as well as building, etc. So let's look at the antenna design and the network planning for 5G. So this is, again, I put this to give a bit of a perspective that how a communication system looks like. If you take the transmitter, you have a data source that could be, your video or your audio, or any files that you want to download and those kind of things. They're, of course, encoded so that others don't see what it is. Then you modulate it, and then you have an antenna that transmits. Then you have a channel through which this wave propagates. And then you have a receive antenna, and then, of course, the reverse process where you actually receive the data, that is your voice or video and those kinds of things. So in this one, we're going to take a look at this antenna side and channel side. When it's a channel, of course, then the name comes from maybe because, if you connect with a cable, that is your channel. But in this case, there's no cable. It has to go through the normal, whatever circumstances you have in terms of buildings or rural areas and the inside buildings, walls, and those kind of things. So how do you take that into account when signal is transmitting from transmitter antenna to the receiver antenna, and what happens in between? That's what normally they refer to as channel coverage. So we'll take a look at a case study, not as much as, this is the best design or anything like that, how you can design some of these antennas, the process of simulations are there, and also network planning in terms of the wave propagation and also channel statistics, beamforming, etc. So coming to antennas, we'll first deal with antennas and then go to the channel capacity, channel analysis portion of the talk. So obviously, these are based on grounding equations, which are Maxwell's equations in our case, with underlying physics. And of course, they're expressed in the form of differential or integral equations. And you solve these these equations applying various boundary conditions. That is actually very critical of a specific problem. So because of this, obviously, we all have dealt with differential equations and integral equations in our math classes, and we know how to solve them. But when you solve them, you have to apply these boundary conditions. So that becomes very difficult. Or for simple problems, if you take a sphere, the geometry equation of the sphere, so you can say these conditions are met, this is the boundary condition to apply. But if you take something complex like, very maybe a car, I guess, or an aircraft or other kind of things, or complex antenna structures you have, it becomes very difficult to put the boundary conditions on them analytically to solve those equations. Of course, this is just as a tribute to Maxwell, I guess I put these equations, but this is the only equations I will show in this talk. Obviously, all these things are basis for all the work we do in antenna analysis, and also extending to the propagation as well to some extent. So we have to be grateful to Maxwell for bringing those equations to us. So this is my short introduction to computational electromagnetics. As we mentioned, we have realistic objects, even you can take the cell phones and ships and cars and those kind of things, and you want to solve Maxwell's equations on them. Putting the boundary conditions on them become very, very difficult because of the geometry equations are complex, and even if you solve for one and then you get the next problem, then you have to go and create the boundary conditions with the next problem and solve by hand. So that's where the CEM tools come into picture, the electromagnetic tools, simulation tools, because they're also not magic, right? They also solve Maxwell's equations. And I'll explain in the next slide how they solve those Maxwell's equations. And so, of course, for the users, these are like a black box, and then you get your currents, you get your radiation patterns, so on and so forth. So you can go ahead with your actual problem solving than wondering about how to solve Maxwell's equations for a particular problem. So as an example, let's say you take a car and there is a little shark fin antenna on the top. Let's say we had to have 1.8 gigahertz LTE antenna there. We start with a CAD model. Obviously, if you were to solve this analytically, you would like to have all the geometry equations and solve the boundary conditions for those geometry equations, applying what is metal, what is material type of thing, which is, as we can see, it's not possible for us to do that. Even if you do that, it's, next comes a different one. You have to solve for that one again. So what numerical methods do is take that CAD geometry and discretize into what we call mesh or discretization. In this case, we are discretizing this with triangular elements. Essentially, what's happening here is that we are splitting this complex shape into very known triangles, there small triangles in the object. So we take these triangles, which in the CEM terminology they're called subdomains. In these subdomains, we solve Maxwell's equations because now we know the shape and we know how to solve it for that particular shape and how to apply the boundary conditions there. So once you solve it, then you can combine all those solutions together to create your currents. And of course, then once you have the currents, you can compute the radiation pattern. But the key is how small or how big these triangles can be. And as this, you can think of as a sampling of your field. So if your field is varying, let's say sinusoidally at a frequency, if you take 2 points, maybe it's too less, 3 points, 4 points. When you get to 6 and 7, now you can see the shape of the sinusoidal wave. So by default, we can say 10 points per wavelength could describe your sinusoidal wave appropriately at that frequency. So that's what makes this the size of the triangle, the determination of the size of the triangle based on the frequency. So what that means is that as you go to higher frequencies, the wavelength decreases, so your triangle size decreases, so the number of triangles you're going to have on an object increases, which means that your computational cost, that is memory required, but also the time required increases. So that's where I guess the solutions come into picture in terms of the FEM or FTTD or metro moments and other kind of solutions. So with that, we offer, of course, this from Altair side, Altair Feko as one solution for such problems to solve Maxwell's equations numerically, but also the wind prop that I already talked about before. Of course, with respect to applications, with these tools, one can solve antenna designs, antenna placement, and electromagnetic compatibility, scattering and RCS and other applications as well. How we're able to do this is by applying various technologies into the software. That means, if you remember, I guess what I mentioned about discretizing the object and trying to solve it using Maxwell's equations. So various methodologies are developed. So these methods can be useful for a specific class of problems. For example, FEM could be very useful when you have a lot of materials. Same thing with FTTD. Metro moments could be very useful when you have metallic objects as well as wires and those kind of things. Adaptive cross approximations could be useful. And of course, as you go to higher electrical size, MLFMM can be very, very useful. solving these Maxwell's equations. So if you notice here, I split them into two parts. One is full wave solutions, other is asymptotic solutions. Full wave solutions means they solve Maxwell's equations accurately in the subdomains that we have. And so you have very accurate answers if your CAD model is correct and also your mesh is correct. That means you did not under sample your fields and those kind of things. And then asymptotic solutions like physical optics, ray launching geometrical optics, also referred to as shooting and bouncing ray, uniform theory of diffraction. They also solve Maxwell's equations, but approximately with some assumptions. So when those assumptions are met, you can solve your problems efficiently with these methods as well. So of course, you can also see these arrows that because you can't just divide these into different kind of problems and say, okay, I can only solve with this FEM, I can only solve with method of moments. So what we have is a combination of them, because you can have part of the problem to be FEM, other part to be method of moments or MLFMM. Same thing is with asymptotic solutions. Part of the problem can be method of moments and part could be physical optics and UTD. I'm not going to go into the too much details here because that's not the topic of the talk today. So coming to wave propagation, these are also Maxwell's equations based in a way, but then they have to deal with this large areas. So we'll talk about this one a little bit later in this one, what kind of propagation methodologies are used, both for, let's say, outdoor as well as indoor. And also when you do this ADAS applications with the cars when they're driving with the radars, as well as industry situations with the complex radio networks and their coexistence, as well as safety of the radio networks. Because that's also critical for us, because a lot of these wireless communications are coming in, a lot of energy is pumped into the our native environment, I guess. Want to make sure that it's not exceeding the safety limits. So the governments have to take care of this so that they're not harmful. So how do these things fit into our scenario here? So let's say you have a mobile device. You can do the analysis of the mobile device with antenna pattern with Feko. Same thing with the base station or Wi-Fi router. And of course, if you have a base station, the wave propagation, you put the base station as a source and then compute the power distribution in a city environment. Same thing with the Wi-Fi router at home or at office. You have this Wi-Fi access points, and you can compute the coverage of the Wi-Fi in the in an office or a home environment there. So coming to the 5G, obviously one can use FEM, FTTD, MLFM, method of moments kind of full wave solutions for the device modeling. And of course, same with the base station. Of course, the base station has the luxury of being a large one, where you can have large number of antenna elements. So one can either use FTTD or MLFMM or both a combination to solve for a base station. Of course, when it comes to the radio coverage, you use the wave propagation there. Now let's get into the specific design side of it. For, let's say, starting with the mobile device. Of course, we picked 26 gigahertz because the lower frequency, there are a lot of designs available, and it's not a new thing, but 26 gigahertz and higher is becoming a new one here. And also, they are very suitable for mobile devices because as the wavelength goes up, the size of the antenna comes down. So you can now easily design an array rather than a single element and be able to incorporate that into your mobile device. Of course, there is a need to achieve high gain, and there should be feeding and control circuits, and also some good isolation between array elements so that we can have a nice array pattern rather than not having to have that there. So we started with a design that was published in a paper back in 2016. That actually is a wideband dipole antenna array in a linear eight element array. So that is this one here we're showing. This is actually a folded dipole on both sides of the substrate. One of the advantages we have is that we can start this design with, let's say, a 2.5D solution. When we say that the substrates are not discretized, so it is an infinite substrate, but then you discretize only these metallic elements, so your computational cost is very, very low. So it lends very well for very quick optimization of your array. So here you want to optimize the self-impedance, that is SNN, and also the mutual impedance, that is FNN, between these things, meaning you want to have this very low, that is at a certain frequency and with a band, but also this one to be low as well for coupling between these elements. So in this case, we used our optimization method called global response surface method. This is actually a global optimization method, and internally it uses what we can term as a machine learning algorithm to be able to do a quicker optimization than, let's say, a genetic algorithm and those kind of things. And of course, we can form this into various cores. And first optimize this on a infinite substrate layers, and then we could optimize that into a PCB with a ground plane, but of course with the dielectric here. And this we used the FTTD to the simulations there. So if you look at the design here, you can see all S parameters for the 8 elements. They are well below -10, around, I think the center frequency of it says 7.7 gigahertz, but that's a bandwidth I guess we have here at 26 gigahertz as a center band. And then the rest of them, these are all the mutual coupling. Probably these are the close enough elements. Then you go a little bit further, then they go a little bit further. You can see that these come down very well. Typically, I think for these kind of things, -15 dB isolation between element to element could be good enough. So you can see that they're all in that range. But also at the various frequencies, the beamwidth, the gain can be varying because of the frequency and the size of the array at those frequencies. And also scanning performance of the array can also be seen at various degrees here, various scanning angles there. So now you want to put 2 of them so that you have pattern diversity in a mobile device. Here, also isolation between this array and this array becomes very critical. And when we computed the isolation, they're all below -30 dB. As we heard yesterday's talk, this is a good isolation between 2 of the elements on a mobile device. And also they provide the pattern diversity because one you have on this side and the other we have on this side. Then one could integrate that into a mobile device. We have done at less than 0.9 gigahertz as well as 26 gigahertz. You can see that the simulation time is very, very close. That's because even though we're doing at lower frequency here, because of the details, you have to capture all the details. So this is something in people who do computational electromagnetics or the simulations have to keep in mind that there are 2 aspects of the simulation when it comes to discretization. One is the frequency, as I mentioned. You have to take 10 points per wavelength or lambda by 10, size of the cell or the size of the element. Also, before that, you should be able to capture the geometry. If your mesh is not able to describe the geometry, then of course your results are not going to be good. So the first and foremost is your mesh should be able to capture the geometry accurately, and then it should be able to represent the frequency of operation that you have, or highest frequency of operation you have. So in that respect, we already discretized, over-discretized this for the frequency. So the discretization did not change much, so you see the same amount of time here as well. So moving on to the base station side here, we did a similar thing. We picked again a paper from one of the published papers, which was actually done at 22 gigahertz, and we re-optimized for 26 gigahertz. It's a loop design, including slot to increase the efficiency there, and printed on FR4 substrate. So we did a single element analysis. Then we optimized a 4x4 array. So we have the coupling optimized as well between those elements. Then, 2x2 element. And then we took this as a subarray and then placed into 4x4, 8x8, and 16x16 to see the performance of them. Again, if you look at this same way as we have done for the hand device, We have the S parameters, that is self, as well as mutual ones. You can see that most of them remain below -15, almost close here, even at 16 by 16. That indicates that the design that we have done at 2 by 2 optimization, array optimization, seems to hold good for rest of the elements as well. So resonant frequency is kept at 26 gigahertz, and the bandwidth is still close to 2 gigahertz here, and the worst case coupling is approximately -15 dB between those elements. And again, different arrays sizes will give you different gains, as you can see, but also the scanning of them at various angles can also be seen. As you see that this is showing both sides, so normally that is not the case. You have a ground plane below this array. So if you put a ground plane, then of course your beam becomes on one-sided. So this is a simulation just to show that the size of the ground plane can affect your side lobes and those kind of things, and also the back lobes, which sometimes can cause interference into your other devices if you have too much back lobe, front to back lobe ratio. So this is what showing that large ground plane, your back lobe is suppressed, as opposed to the ground plane that we have just covering the array itself. So you can also, because these simulations we have done as a complete, what we call as a whole problem, meaning you apply MLFMM or you apply FEM to this problem and solve the whole problem. Instead, that could take some time and memory. So instead, one can also apply different techniques to solve them more efficiently. One of them is applying periodic boundary conditions. What that means is that let's say you have this helix element here, you apply two-dimensional periodic boundary condition on this, so that it is as though mathematically we are extending this to infinity on this side and infinity on all these directions. That means you have an infinite array. But people may ask, what's the big deal about infinite array? Because we're not going to have an infinite array. One is characterizing the element in the array environment that can give you some good insights into the design, but also using this single cell element here, you can use array factor and phase shift or the beam scan angle, as well as the number of elements specification. You can actually look at in a way, approximately the finite array analysis results as well. But of course, it saves the memory for you. It's done in less than half megabyte compared to 4.5 gigabytes. So we're not saying this is a final solution, but this can serve as a design tool where you can do quick simulations for that. So if you do that with the array we talked about, specifying the scan angles in theta and phi, as well as the number of elements 8 by 8, now we could be able to compute using PBC as well as the array with full analysis. So there is some differences, but it is close enough for you to do an initial design. Same thing with the scanning as well. Then we have, if you don't want to use the PBC, for example, one step after that would be finite array analysis. And there's a technique called domain Green's function method. This is published in IEEE transactions on AP in 2014, and this is implemented in our software, where if you have an identical element like the ones we're showing here, we can actually compute one element at a time because they're all identical. So they're in method of moments terminology, their impedance matrices will be identical. But of course, they have coupling between them based on the distance, so that could be different. So somehow this technique actually compresses this whole matrix into a diagonal matrix elements. So you can solve them very easily. And when I say easily, I guess when you can solve them with a less computational effort, that means memory and time. So you can do quick design of these finite arrays that take edge effects also into account, as well as some mutual coupling into account as well. So with this one, you can do a linear array like this one, two-dimensional linear array, or even a cylindrical array, the one we're showing. So it doesn't need to be conformed to any type of regular configuration like we normally do with PBC. PBC requires that these are all spaced at a certain distance, whereas here they can be at any distance or in arbitrary configuration. Of course, saving the time, 1.5 hours to 30 minutes here, and 7 gigabytes to 320 megabytes here. So that's a good amount of savings in memory. So that's about antennas. So let's go to the radio channels, channel coverage here. So we look at the wave propagation models in this section of the talk, beamforming for 5G, and of course, the planning purpose, and as well as envelope beam pattern and Monte Carlo simulations applications as well. So when it comes to propagation, this is also somewhat dependent on Maxwell's equations, but with very approximated equations, way beyond what we can call as asymptotic solutions in the previous section of the talk. So if you have to do three different scenarios here, for example, rural propagation, urban, and indoor propagation. Rural propagation, you need the topography pixel data. That's what we take. Optionally, you can have clutter losses and heights and ground properties that can be put into the software. And then we use various empirical formulas or more rigorous, what we call ray tracing algorithms. Empirical formulas are the ones that are, by measurement campaigns and all, they come up with, you measure at various locations and you come up with a empirical formula that probably can apply to most of the rural scenarios. People like Hata Okumara and also ITU, International Telephone Union, they have their own models that one can use. These are what we can call as a back of the envelope calculation. So they're very fast, but in many times they may not be as accurate and complex kind of thing. Then we have standard ray tracing method. This is actually applies what we can call as a UTD kind of application, where or geometrical optics kind of application, where you can compute the reflections, you can compute the diffractions, as well as transmission through the materials and those kind of things. And then we actually have a proprietary method called dominant path model. So when you do this standard ray tracing, let's say you are launching, I would say, thousands of rays. So each ray needs to be traced and then from the transmitter to the receiver. So that can take a lot of time based on how much complexity you have in your model. But what we notice is that when you do this, most of the energy is focused into a few rays. So why do all the rays? So you can discard the rays that don't carry much of the energy and do only the rays that carry dominant power. That's why you call dominant path model type of thing. It saves the time dramatically and can give you results very reasonably accurate compared to standard ray tracing. Then when it comes to city environment or urban environment, you can have 2.5D building vector data, and from there we can bring up the 3D models. And also you can have material properties, and you can add topography, because the earth may not be flat in some cases, and vegetation and its losses and those kind of things. Same here, dominant path model. Also, we include what's called intelligent ray tracing. If you remember the standard to intelligent, what intelligent ray tracing is that you pre-process the standard ray tracing, so you know the paths ahead of time, so you could do much faster post-processing of these things when you do the calculations. Same with the indoor type of thing. You need the 3D vector data so that you can have the building, the architecture of the building and the inside configuration, and material properties for the walls as well as furniture and so on and so forth. And this also has a method called direct ray models. It's called multi-wall. So this is a very approximate method where basically it assumes that the ray is passing through various walls, and you assign the attenuation each wall so that it can compute very quickly. Or you can go through our standard ray tracing or intelligent ray tracing, including the dominant path model for these applications. So coming back to our thing, so those are the kind of categories we can think of. But here, when you think of other scenarios, when the propagation model, you can think of it as a macro cell, micro cell, and pico cell. Macro cell is where it's between 30 kilometers and 2 kilometers. And similarly, this is similar to a rural environment. So you can see that these are the propagation models that are used. Microcell is between 2 kilometers and 200 meters. This is similar to our, let's say you can say urban scenarios where downtown type of thing. You can use this type of analysis here and the propagation models here. Picocell could be indoor or very small cell, less than 200 meters. And again, one can use these models for your propagation. So when we say these models, I guess, as I mentioned before, some of them are empirical, so they could be very fast, but they could be approximate. Some of them are based on ray tracing, which could be a little bit slower than, they're also very fast compared to, let's say, when you apply FEM or physical optics and those kind of things. But they could be slower than approximate formulas, the empirical formulas, but can give you more accurate answers for you. So in 3D ray tracing, what are the things we need to look for? If you look at the transmitter here and your receiver here, you can see here that there are reflections that are going from this building and coming back here, and there's a direct ray and also other reflections coming off of here. And even these ones, not only coming directly here, they also bounce off from the ground and come here. So your propagation model should be able to take all these things into account, that is reflection, diffraction, scattering, and shadowing as well. And different delays and attenuations should be able to be computed, because that's what when the communication system looks at it, they're all not coming at the same time, not with the same angular diversity and those kind of things. So your communication system should be able to take care of them. So you should be able to compute those quantities. And also there is a destructive and constructive interference, and also dependence and frequency based on what kind of bands we're using, low band, mid band, and high band here. So if it's a no line of sight, what is called a Rayleigh fading, that could be there. This is without line of sight. A line of sight one can call as a Rice fading. Of course, these are also by equations, you can compute these things, but also by using the ray tracing, they are automatically taken into account. So what happens in the ray tracing when you have, let's say, a transmitter on the below rooftop level, that is similarly the case for the 5G, because you don't want to put on the top of the roof of a tall building where it has to propagate for a longer distance. So if you put in as a lower height, for example, even in 5 to 10 meters height. So what happens is that there is a street going around here. You can see most of the rays are within the street. And of course, there's some going around and coming back here. So if you just look at the direct rays only, that is rays coming from the transmitter to the receiver, you can see all of them are concentrated in the street. And if you take single reflections, still doesn't make any difference. And if you take single diffraction, now we can start seeing various those diffracted signals going around into the other streets as well, and of course double reflection as well. Double reflection also doesn't seem to. So diffraction makes the difference in how the coverage can be computed in these kind of scenarios. So for the greater than 6 gigahertz computations, you should obviously, the transmission becomes important, reflection also becomes important, but diffraction doesn't seem to have a lot of effect, because diffractions are minimized as you go to higher frequencies. Then there is a scattering, and this scattering also becomes critical at higher frequencies, because roughness, because now the wavelength is so small, even the surface roughness can play a role. That roughness can create what we call a diffuse scattering. So your model should be able to account for the diffuse scattering when you're doing these calculations. Then comes our attenuation due to the nature here. There are two types of attenuation at higher than 6 gigahertz frequencies. One is the atmospheric loss. This is the oxygen absorption of the waves. Second is the rain attenuation. You can see that at lower frequencies, maybe it's okay, 0.1 dB per kilometer at 30 gigahertz, but at 60, for example, it's 20 dB per kilometer at 60 gigahertz. So again, it peaks and then goes up, peaks and goes up. And so that's one of the difficulties you have with higher frequencies is the atmospheric absorption as well as the rain. Here you can see that there's 1.4 dB attenuation for 200 meters at 20 gigahertz. With, of course, the rainfall, because this chart actually gives you what is the rainfall level, and pick a heavy rainfall. So this is something we don't want to have, right? When you have rain, we don't want to have our communications being disrupted. So this is where the low band, mid band, and high band come into picture, where you can apply appropriate frequencies for appropriate scenarios so that your communications are not disturbed. So coming to the beamforming side, this becomes critical in 5G because now with the Omni patterns, we saw that even if you use MIMO, you can't attain the data rates that you want to attain. So now you want to use the beamforming, so you have a focused beam that can be coming your way, at your device way. So that can be done with the beamforming and also spatial multiplexing, that is scanning the beam in various directions so that you can serve many users at the same time. So when you do that, you have to take these what we call channel statistics into account. That is the delay spread, which we'll talk in the next slide, angular spread at both the base station as well as the mobile station, and angular spread in the elevation and azimuth as well, and cumulative distribution function. Because most of these things are going to be statistical in nature, meaning they're not deterministic most of the time, because every scenario can change. So you cannot say, I just have this one and it can be a deterministic problem I can solve and deploy it, because every scenario can be different. So they come up with the statistical nature of these quantities that can be used in your communication analysis. So in terms of channel statistics, if you look at this chart here, this computes what is the best cell to use for a certain area. For example, if you take the green one, this is the site that can be used for the green, and the blue one, this is the site that can be used, the base station site that can be used, so on and so forth here. But if you zoom into this, you can see there's a transmitter here, and there's a transmitter here and the receiver here. And so the rays are going from, obviously there's no direct line of sight here, so they have to go around to these reflections and those kind of things. So that can cause a delay spread. That means each ray can arriving at a different time. So ideally, we would like all of them to come in the same place, same time, so we can know what the signal is. But there is a delay spread because of the multiple reflections. And this shows that is a, I don't know whether you can read this or not, it says cumulative probability. So if you take 0.5, 50% probability, there is a 150 nanosecond delay spread. Same thing here with the angular spread at the base station and the angular spread at the mobile station because of that. Because base station, when the uplink comes in, and mobile station, the downlink comes in there. So these are the quantities one would look for in simulating the channel characteristics. I'm not saying that these are good numbers or bad numbers. I'm saying when you do the channel modeling for the communication system, these are the things that you need to look for as well, in addition to power and those kind of things. And then one more thing to see is the effect of the beam width. For example, here on the top, what we're showing is that there is a 4x4 antennas on the base station, and you can see that when these two users are a little bit far away, there's a good amount of connection to this and isolation to the other user. But when they come very close, it becomes kind of mixed, I guess, here. So when you use 8x16 by 16 elements, then it becomes very narrow beam. So that's the effect that the beamforming has, and that need to be taken into account in terms of your design as well. What are the who are the customers you're serving, and how much beam width should be suitable for you. Coming to deployment scenarios, if you have wide area to be covered, you use the 3.5 gigahertz, where you can see that these are the base stations, by the way, these little dots here. You can see the most of it is covered very well if you look at the power, received power levels here. But then when you look at 26 gigahertz, you can see that there's a lot of blue areas, that is very, very low signals for the same number of base stations. This is doing, maybe go to the next one, I guess. If you look at closely, this is only transmitted to 4x4 antenna array, not using the beamforming on the base station, on the mobile station side. So if you were to use both, that means both on the base station side and also on the mobile station or the cell phones here, you can see that now you are able to cover the whole thing. So this kind of brings the point that when we use massive MIMO, it has to be on both sides to be able to cover most of the area, or you will be restricted to very small areas to be able to do that. I know we're getting a little bit over time, but I got a few more slides and I should be done with the talk. So then again, in the beamforming, you have multiple beams, but also you can use what's called envelope beam pattern, where there are static loads, that is, constant traffic. When it's the traffic, I guess the communication load, I guess, that we'll have on those things. Or you can also do, so this analysis can help you when you have static load, what would be your connectivity rates and those kind of things. Then we have multiple individual beam assignments. So this is what one can do a Monte Carlo analysis to find out what was the probability that, how much connectivity can be assigned to different users. So I won't go too much into these things because I'm also not, this goes into the what we can call as a communication theory side of it, which I'm not very an expert on. So one can choose in the software, for example, static simulation, that is the traffic is homogeneous, and also, of course, another location-dependent traffic, and you can assign various sites with this type of thing. And in this case, we consider multiple beams, but that are scanning. But then you consider the envelope beam pattern as, so it's not focusing on one user, but it's focusing on area, so you can take care of the larger area or the larger traffic at the same time. But then when you have a situation like this, for example, where you want to cover individual users, for example, the users could be voice users that are just talking, and our video users are data download users in orange, for example. So this is kind of one scenario. But then how do you know this is not going to change? Because it's a very time dependent kind of thing. It can change anytime. Like people can be moving here, moving there. So you have to do a Monte Carlo analysis to make sure your sites can cover all of your voice applications and video applications and data load, and of course with the priorities, right? Voice can be, if there is a short break, maybe it's not that big of a deal, but video and data, you want to make sure they have high data rates, so that you focus on them more time than maybe on the voice side of thing. So that analysis is also very critical in doing that. Of course, going deeper into the communication, again, I'm not an expert on these ones, but I wanted to show you that the simulation capability can go much beyond the electromagnetics into communications, where you can calculate the data rates as well as the channel capacities and those kind of things. While we could do that very well with let's say the 4G and those kind of things with the MIMO streams, but when it comes to 5G, you still have the MIMO because you can use multiple streams to be able to compute the connectivity and those things. But also they introduced what is called numerology, that is a term mu, where what I understand is that mu equal to 0 was for the LTE type of application. It is right now with the 20 megahertz bandwidth with the 15 kilohertz subcarriers. So you can fit in many channels into this 20 megahertz bandwidth. Now they have increased that into mu equals 1 and 2 and 3, which I understand that mu equals 1 means 50 with the 2 to the power of multiplied by 2, 15 multiplied by 2. Mu equals 2 means 15 multiplied by 2 square. And same thing here, 15 multiplied by 2 to the power of cube. So that's how they want to increase the subcarrier spacing or slot length, they can call it, Then, of course, you have 20 megahertz. If you have 20 megahertz bandwidth, you can go up to this 60 kilohertz mu equals 2. Then, of course, 50, you can go higher. Same thing with 100 megahertz bandwidth, 200 and 400. So in the software, we have that capability where you can choose what numerology you want to use, and we will be able to calculate the connectivity or the channel capacity for your calculations. So in conclusion, you can see that 5G provides higher throughputs and also will introduce new applications that are not currently possible. So for that, there's a massive MIMO usage and higher frequency bands need to be used. What we're trying to say here is that you have to use a reliable simulation tool for your antenna design so that all the details are taken into account, and also the ease of design flow, I guess, going from 2.5D to PCB and also integrating into design. All those things need to be able to be done. And then more importantly, not only stopping at the antenna design, going further into radio channel and coverage analysis with high accuracy using these 3D ray tracing models and also network planning. So because we can also compute the connectivity and data rates and other kind of things. So that's the proof in the pudding kind of thing, right? You do the antenna design, but then you deploy it into the city or you deploy into the rural area. You want to know what is my connectivity. That is the key, I guess, at the end. People don't care how good of a pattern we have, or how good of a S parameters we have. At the end, can we get the connectivity or not, and can we get the data rates or not? That becomes very important with the radio channel coverage. So that's a complete simulations one can do using these tools. So if you're, of course, I'm going to little plug with the software here. If your students or faculty in the audience, we provide a free student edition, which is a limited, but at the same time should be good enough for you to play around and do some reasonable things, both for Feko as well as WinProp. You can download them from altairuniversity.com. This is our academic site where you can download. But also you can download a free ebook that can give you the basics of the learning the tool, the Feko tool that we have also from our Altair University website. Then as Mahesh mentioned in his introduction, we also published a book on this one, Antenna Analysis and Design using Feko EM Simulation Software. My co-authors here, Professor Atif Al-Sherbani and Professor Payam Nayeri, they are from Colorado School of Mines, and we collaborated with them to publish this book maybe 6.5 years ago, but still very relevant, I guess. So if you look at the contents of the book, they're like any antenna book. This is not a Feko training book. This is actually an antenna book where you can use a tool like Feko to learn about antennas. Because if you take any antenna book, a lot of equations and a lot of fundamentals, which I think is required for the students to learn. But if you're a practicing engineer, you're a communication guy, you don't want to go through all the math, you just want to know how antennas work and play around with them, you can use this book to learn different type of, or if you're a undergraduate student where you don't want to, essentially eventually you learn those basics, but you want to play around and also have complex scenarios, you can use this book. And also I want to say that any of the practicing engineers nowadays, antenna engineers, they very rarely use analytical equations to design an antenna. They always, I would say 99% of the practicing engineers use one simulation or the other. So this can help in understanding antennas through simulation. And one last slide here is we are hiring in India actually a senior application engineer for electromagnetic solutions. If you have a good background in electromagnetics with 6+ years of experience doing various things, you can actually send your resume to Ramesh Baswala at altair.com, or you can look up our career site. We have many more openings at the career site. This is, of course, our main emphasis now to beef up our electromagnetic capabilities in our Indian operations. But also, of course, we have other opportunities at altair.com/careers. course, you can contact me if you have any questions. Or Manoj, my counterpart in India, Manoj Mangarajani, in our Bangalore office or Pune office. So he can help as well. With that, thank you very much for your attention. And we have a website dedicated to 5G at altair.com/5G. With that, thank you again for your attention, and I'm open for questions.
Thank you so much, sir. It was a very interesting talk. So now we'll take some few questions. So the first question I've got is, okay, so when you are doing analysis for these channel models for a stationary antenna, you show that you have one map. But if it's going to be a mobile antenna, how many maps are generally needed, and how do you make sure that the scenario will be same for everything? All kinds of scenario, how do you simulate all these things is what they're asking.
It's a good question, I guess. So if you come to, let's say, a map like this, where we are taking a city map, right? And we normally, what we have done, obviously we don't supply these maps, but these maps are available in various ways. One way is you can go to what we call a U.S. Geological Survey site, where they have maps from different cities, not only in the US, but also in other countries as well, but maybe at a little lower resolution that you can get and download them for free, and we can import them into our software. And the second way is openstreet.com. This is actually, or maybe openstreets.org, I guess. This is a public or open source street maps that are provided. So you can take any downtown areas and almost like a Google Maps, I guess. Not same as Google Maps, but it's a separate organization where you can download those maps, a certain area, and then use in our simulation tool. So then you can simulate not only one city but different cities and different scenarios there. But of course, there are also commercial map vendors. These people have very high resolution maps, even 1 meter or less than 1 meter resolution of the maps that you can, of course, you have to buy from them, and we can import some of those maps as well, and you can use them for your analysis.
Okay. So next question is, can machine learning be used for these kinds of analysis, or if so, how well can it be integrated, and how can we understand its usage in these things?
Kitapaya, if I understand correctly, are we talking about machine learning for the wave propagation or for the antenna design?
For the simulations, I think they're asking. So can machine learning be used, and how can it be used or integrated with all these kinds of simulations is what they're asking maybe.
Sure. It's a good question, I think. Yeah, machine learning is nowadays is becoming very popular, right? Everywhere you see machine learning, or you can call it artificial intelligence. These are becoming not only buzzwords, but also becoming very relevant in our day-to-day lives. Like even, for example, if you take the COVID situation, all the dashboards they have, the predictions they do, you can all think of as a machine learning process, I guess. They are artificial intelligence process by taking various things into account. So basically what machine learning means is that you create the data that with which the machine can learn. So this data could be coming randomly, like for example, COVID data, I guess, coming from various places. We're not controlling the data, I guess. It's coming in, machine learning algorithms figure out where this is going and then do the predictions type of thing. But in the simulation side, we can control the data. So if you take an optimization, for example, we can say, I have 5 parameters in this particular problem. Those 5 parameters need to be varied so that I can get an optimum solution. That's how the optimizers work, right? So, but in this case, what we have to do, what machine learning does is that, okay, if these 5 parameters are there, I can randomly change these 5 parameters, or I said randomly, but there's an algorithm behind it. So with a minimum number of simulations, I can figure out what this particular simulation is doing. So once it figures out, what that means is that it creates an analytical model for your physical situation or simulation. So once it figures out that formula, then it can take it further with that analytical expression rather than using your actual simulations. We have done some work in that area. I actually gave a short course on this machine learning for antenna design at the last APS conference, which would have been in Montreal but was virtually done. And we have it on our website, actually, all the 3-hour workshop that we provided. We have another tool called HyperStudy in Altair portfolio, and where it actually can implement machine learning for any type of data, including, let's say, in our case, Feko. So we provide the parameterized model of an antenna or any structure you have in your problem, and HyperStudy reads that one and uses its internal algorithms, which are, by the way, known as the design exploration or design of experiments. With those algorithms, it can form an analytical function for your model. Once it forms analytical function, it can throw away your actual EM simulations and use that analytical function with those variables to do optimization or anything you want to do. Even you want to do statistical analysis with tolerances with millions of simulations. Because this analytical formulation, there's no time, meaning it's all in seconds. Few seconds you can get your optimization done. Few seconds you can get your statistical analysis done. So I think same thing can be applied. We have not done it yet in the propagation side, but I think that's also possible on the propagation side, where you provide the data from the simulation, and basically the software will figure out what kind of data it has to collect from the simulation and use it for machine learning.
Okay. So I think next question is based on the current slide which you have. So what are the challenges or the limitations in doing beamforming in the mobile?
You mean like this one here?
Yeah.
So probably if you attended yesterday's talk, I guess Deep and also Satish talk day before yesterday, in the mobile device, though I'm showing here nicely 2 arrays, right? At going at 26, working at 26 gigahertz. But then what happens in the real scenario, we don't have phones that just work for this frequency. We have phones that has to work for all frequency bands, so that any scenario you're in, even today, I guess when you use 4G, 3G also should be supported. Maybe 2G is phased out, but then you have GPS antennas, you have other type of Bluetooth antennas, Wi-Fi antennas. So it gets very, very complicated in incorporating all these antennas into the device we have, or also these devices are becoming thinner as well. Those are the challenges I see. The space is an issue. And most of the time what happens is that, though we are showing here very nicely these arrays and those kind of things, most of the time we are also competing for the real estate in the mobile device. By that I mean, we have again, cameras that are there, and battery that is there, and the processor they have to use, and associated, the whole PCB that is used is occupied by hundreds, if not many more devices and other kind of things. So where do we get the space to put in all these antennas into the mobile device? That's a big challenge that fortunately I don't have to deal with personally, but our customers and the mobile device areas deal with. So one solution they found, or the solution that came about recently, is what we call characteristic mode analysis. Probably some of you heard about this term, CMA. So basically what happens is that what I was told by some of the people who do this kind of work is that when the PCB is done, whatever space that is left over is given to an antenna engineer and say, okay, what are this space, this may not be a regularly constructed space. It could be very arbitrary shape. Go ahead and make your antennas in this space and make sure that they all work, right? What characteristic mode analysis will do is that if you take that arbitrary shaped shape with a conductor or something like that, and what kind of modes that shape can support. here we're not talking about the cavity modes and things like that. We're talking about open radiating structure and its modes. And the characteristic mode analysis through Metro Moments matrix, the impedance matrix, can give you different modes that particular structure can support. Here also, we're not talking about the structure with an excitation. This is a structure with no excitation. It's a naturally supported electromagnetic modes can be found out. So if you do that, based on those mode behavior, basically now you are able to understand the physics behind the structure. So in the past, what people have done is that they arbitrarily use optimization or excitations. By intuition, they say, okay, this shape could support something like this. Let's put something there and put some slots and do the brute force simulations to find out what it can do. Now, before you do that, if you can do characteristic mode analysis and understand the electromagnetic behavior of the structure, you may be able to come up with a better design and more efficient design in a shorter time than doing the brute force way. So that's some of the things that are going on with the characteristic mode analysis. And we support that analysis as well in Feko. So if you like to do that, to do what we call, actually we published an article on this one in AP magazine, IEEE APS magazine. We call it putting physics into the simulations, because in the past or even now, I guess most of the simulations are done by people with, I would call it not, when I say I'm not broadly characterizing anybody here, but most of the time, especially students starting out, I guess they do more of a brute force way and then say, okay, throw something at the simulation, whatever it gives, we accept the results. Whereas this one actually shows you what happens in the structure physics-wise, the mode currents and mode patterns, etc. Now you can use that knowledge to be able to design a better antenna for you.
Okay. Thank you, sir. That I think we can take one last quick question. So, when you talked about domain green function method and you told that it occupies less memory, so what kind of compromise has to be done in the accuracy of the final results when compared to other methods?
So I would say, when you say other methods, I guess there's only two ways to do this finite arrays, I guess. One is taking the whole array and then analyzing it. For example, if you look at this one here, you can put the whole thing in there and do the complete analysis. That's, of course, the most accurate way you can get your results. The second way, we don't have it, but in some software, they have it, what is called domain decomposition method, where you can split this into various domains. And then, of course, the approximation comes there, how you match these two domains, the meshes and those kind of things. If you can match them accurately, then you will get a very accurate answers and those kind of things. But what we have here is actually reworking the math, where this Z11 is modified to account for the coupling from, let's say, antenna 2 and antenna 3. So as you can see in the simulations, there is a little bit of approximation, because this modifying this obviously cannot be done without some small approximations. So I would put this as between, if you were to take the domain decomposition and the, of course, then there's a third one is called PBC, right? The periodic boundary conditions, where we can put a number of elements and all those things. If you take accuracy-wise, I would say the full analysis is obviously the most accurate, because you are putting everything in there and doing the calculation. The second comes DGFM, because it's also not doing any approximations, but maybe modifying this matrix might have some approximations in there. Third one could be the domain decomposition, and fourth one could be the periodic boundary conditions, because periodic boundary conditions, they don't take mutual coupling into, maybe mutual coupling, but not the edge effects and those kind of things to account.
Okay. Thank you so much, sir, for your answers and your talk. It was very interesting for us to listen to this. And we have with us Chandrakant Kumar sir is there, and Dr. Devdeep has joined us today, and Dr. Satish Sharma is also there. So if the panelists want to say a few words, I welcome them to say a few words here.
Sure. Sure.
Yeah, can I start?
Yes, sir, sure.
Dr. Reddy, sorry for joining late today because I got up in office. So anyway, as I see the enthusiasm among the speakers, I mean, among the participants are still there. It is almost very close to 200 today also. And what I liked about all these three talks, there is a good continuity in what was started from the Professor Satish Sharma, then yesterday Dr. Sarkar, and today. It's a very nice continuity. So if somebody follows from the first day, it's a good concept. And as I see the next sessions, it's takes care of the circuit aspects also and then measurement. So it's a complete package. And all you eminent speakers have made it very nicely organized. Means one handshaking between the speakers are also very nice. We must thank you, all three of you, as of now, for your wonderful effort. And I see the speakers, previous speakers, Dr. Professor Sharma and Devdeep also joining. That's a good sign. And I hope that participants also are having very exciting time because the type of questions they're asking that shows everything. And in the meantime, I request them also, if you want to have anything extra, please try to give us feedback so as that we can plan those things in maybe quickly in next couple of months. And with that, I'll hand over to others panelists. Please say a few words.
Also, from my side, I guess Chandrakant, I think, is very nicely arranged talks. As you can see, even though it's not pre-planned, they worked out that way, right? Satish starting with a very high-level things, and then, of course, Devdeep yesterday continuing the same trend on the antenna design. Of course, me today more on the what I call rubber meets the road. This is where everything happens, I guess, the simulation side. That's also becoming very, very critical nowadays. So thank you very much for all of you, KTPriya and Mahesh, and of course the IEEE AP chapter there in Bangalore, very active. I know I worked with Puneet also in the past. When I came in 2017, I guess IIM conference. So congratulations to you all. And of course, the positive side of COVID is that now we can have these events any time of the anywhere in the world, right? Without any restrictions of travel and being physically there. Obviously, there's a missing part is physical interactions and the lunches we have, sit and talk, other kind of things.
Yeah.
But we have to take both pros and cons and, in a positive way, I guess. So thank you very much all again.
Yeah, so I would
Professor Sharma?
Yeah, I hope I am audible.
Yes, Dr. Devdeep, you're audible.
1 minute. I think Professor Satish Sharma is trying to speak something, but I think you are on mute or your audio is not connected. Can you connect your audio like you did the first day?
Satish sir, your voice is not audible.
You have to connect your audio device.
Meanwhile, yeah, Dr. Devdeep, if you want to say a few words in the meantime, you can, yeah, please.
Yeah, sure. I think there is some issue at Professor Sharma then. So I think first of all, I would like to thank Dr. Reddy for this wonderful presentation and attended it from the start. And it was full of a lot of new information, and I learned several new things. And probably I would like to interact with you later through emails or maybe through some meetings to learn more about them and maybe collaborate or at least do some of the things that we are also working on, like let's say this propagation modeling and combining some of the ideas of antenna design, as I was trying to present yesterday also. So I think Feko the solutions that Altair provides that could be really useful, and my students and the others working with me might be more interested to explore these things. So I will maybe contact you later.
Sure.
But there were a lot of new information, and I would like to hear you. I think probably you are also having another talk very soon. So I would like to attend
this weekend. Yeah.
that also. Yeah. It would be great. Thanks again.
Thank you.
Professor Sharma, can you go to the?
Yeah, I think it should be working now, right? Can you hear me?
Yeah.
Okay,
Kindly go ahead.
So I think.
Good morning, Satish, by the way. Early morning there.
Yeah, good morning. Yeah, I have an NSF panel to serve, so I'm just had to wake up early anyway. So it was very nice talk, Dr. Reddy. It was, and sorry that I couldn't attend your talk yesterday. I had other meetings, So I think one thing with these talks, of course, for the future researchers, engineers, that's the whole purpose, right? We are trying to give as much possible. At the same time, we are learning together. So 6G is also coming, right? So we are already in 5G. And if you go 6G, your challenges will be much more difficult, right? In terms of simulation, computation, and the planning, as well as the, in terms of frequency management, because people will go to terahertz frequencies, or they will go to 300 gigahertz range to have lots of data throughput. So the challenge is coming. So basically another 10 years, you'll have a new set of problems. So I think it's better that we keep engaging ourselves and keep learning. I think
one comment I want to make, Satish. I think these are good things for us. Problems are good things for us, right?
Yeah,
if all problems are solved, why do they need engineers? We want more problems so we can solve them.
Mm-hmm. Exactly.
Challenges, I would say we want challenges to be solved. So.
Yep. So we have plethora of problems to solve and learn a lot. In coming 10 years, more exciting, of course. Thank you, guys.
Thank you. Mahesh, can you switch on your video? And Madhavan sir, if you want to speak something. He is not connected to audio. So Mahesh, it's over to you.
Yes, sir.
Now is it connected? Very much.
Madhavan sir, please go ahead.
Yeah, this is excellent talk. In fact, people generally talk only on the antenna side. Now, today we heard about the other aspects also, where we had to need to take into account this propagation and the types of models.
Sir, we lost you again.
I think there is some network issue because I'm seeing some low bandwidth condition I'm seeing on its screen. Yeah.
Sir, we'll get back to you maybe tomorrow. We'll try to get your this one. I hope you'll be there. So Mahesh, can you go ahead?
Yes, sir. We'll take this opportunity to thank Dr. C.J. Reddy, sir, for accepting our invitation and delivering a wonderful talk. Thank you very much, sir. From AP-MTT Chapter, we'd like to thank you. Thank you very much.
For the opportunity from my side as well. I enjoyed giving the talk.
Mahadevan sir is back.
Mahadevan sir, can you?
Yeah. Now, what I was trying to say was the propagation aspects were also included today, along with the antenna array designs. So array designs, anyway, we saw all the things. But this is a very important thing, because ultimately, as what he put is the customer wants the signal to be there with him. Whether which method you are using, whether you are using MIMO or not, etc. What he wants is finally the signal in his place. If the signal is not there, everything is useless. So the models which you have proposed, both the Ricean model as well as the Raleigh models, they are one, and I'm sure there must be much more models, and some of the students can take up work on this and then really get into more into this, as well as it will be useful for 6G also when you go further. So thank you very much for a very illuminating talk today.
Sure, Mike. And one thing I noticed is that in the education side of this one is the propagation falls under electromagnetics It's connected to the communication forms in the communication theory. So if you go to most of the wireless labs, they don't teach the propagation, they teach the communication theory. I think it has to come together so that they understand what propagation, and also from our side, antenna designers, we stop at antenna and then say we got a nice pattern, we got nice S parameters, but then how does that behave in a propagating environment? So it becomes kind of a what I call a mixed or combined multidisciplinary type of thing, I guess.
Some basic ideas about propagation is taught along with antenna theory nowadays, but that is too preliminary. But they have to get into more details. And if you give a elective on this, people don't take. See, people, once they get a basic course, they want to specialize on the areas of interest. Yes. So we have to really get into these areas and then so.
Yes. Thank you very much.
It can be adopted.
Yes, sir. So I must thank you all, Professor CJ Reddy, Professor Sharma, Dr. Devdeep, and Madhavan sir. Wonderful seeing you after a long time. And Mahesh and Kirtipriya, your kudos to you for organizing this one. So probably with this, we'll close today's session.
Just one thing for the participants is tomorrow. So till today we had talk on antennas. So from tomorrow we are moving on to circuit systems and measurement aspects. So tomorrow we have Dr. Vibhudatta Sahu from IIT Kharagpur. He is going to talk about ADCs and 5G, how they can be, what are the challenges in the ADCs for 5G. So from tomorrow we have interesting talks on circuit. So same time 6:30 p.m. Please everyone log in. You will get the reminder mails again. So thank you all. Good night.
Good night and good morning to you.
Good night and good morning.
Thank you. You all have a nice time. Good night. Take care.
Thank you.
Stay safe. Bye. Bye.